We're going to do practice exam 1 here. Just quick notes. 1, I was told by Nick that he told everyone at the review session, so I guess I can say it here. But there's no NMR and there's no directing groups for electrophilic aromatic substitution on this exam. Directing groups for Diels-Alder is still fair game, so you still need to understand how they work. But for electrophilic aromatic substitution, on where the next substituent goes, it's not there. Second, I just made like the problems I had off the top of my head, but I don't have any more time to make more problems, so this exam may or may not be as long as like your normal exam is going to be. So for this first problem, which molecule is more basic? You draw the lone pairs, of course. The lone pairs are going to be more basic. And what you see is this is 2, 4, 6, 8, 10 electrons. 2, 4, 6, 8, 10 electrons. But this one is not using its lone pair to be a base. So the conjugate acid, I guess it would be in this case, you just take an acid, right? This is still aromatic. This now is non-aromatic. But this is aromatic and this is aromatic. So you lose aromaticity here. So this is the better base. All right, explain these results. You get these and you get 100% this, 0% that, right? And we had a problem like this, I think, that Dr. Davis did in class. So I'll just switch pens. So the first thing I want to do is I want to draw my resonance and see where my partial charges are. See if you hear my precious daughter in the background reading a book with my wife. Right, so we got a partial positive charge there. And then for this, I'll just redraw this so that you can better see. Right, positive and negative ends come together, which is why I get 100% that, 0% of that. So I would explain this by saying partial charges. Wow, that's great ink. I'm probably grade too many people's things. Charges attract each other, forming first product in much greater abundance. Right, something like that. So that's how I explain problem 2. All right, explain these results. So this is a diene, we're adding HBr, and we're doing this in hot temperatures, which usually means what? Thermodynamic. This is the major product, this is the minor product. These two are not observed. So let's just look at this. I'll do these in different colors. If I do the black, I should get this carbocation, which would have a resonance structure. Like this, right? If I do this with green, right? I'll get a positive charge there. And I'll get there. So let's see. Nope, red's not working right now. So this one's going to this product. This one's going to this product. This is going to the minor. And this is going to the major, right? So this question is asking, why is this carbocation more stable than this? And I'm going to explain this with this lone pair giving me an extra resonance structure. So I'm going to say extra lone pair makes the left intermediates more stable than right, which favors the left products. You might think you're done, but you also have to say heat favors top left over, I guess, bottom left, right? Because it's the thermodynamic product. So you also have to say why this one's major and that one's minor. So, okay. In the presence of acid, the NH2 group becomes an electron changes from an electron donating group to an electron withdrawing group. Draw the important structure and explain this phenomena. Okay, so we're in the presence of acid. Okay, we're gonna protonate this nitrogen. I would not stress super hard about this because we're not really doing directing groups on a benzene ring, and I don't think we ever talked about this with Diels-Alder. So I wouldn't stress super hard about this question if you're like, really don't understand it. But remember, this becomes an electron withdrawing group. Also, it will become a meta-director. But remember, the reason why this is OP director, this is going to be a meta-director and electron withdrawing group because N has a positive charge and it no longer has a lone pair to donate electrons into the ring. So that's the thing. So do the important structure and explain the phenomena. All right. 5. Draw the products of this reaction. Remember, we kind of use this H2 in palladium several times. It will not reduce a benzene ring. It will reduce a nitro group. It will reduce the benzylic carbonyl, but not the ketone that's way out there. So this should be your product. It will also reduce ketones and alkenes and alkynes to alkanes. All right. The sulfonyl group is a meta-director and is observed that it reacts in electrophotochromatic substitution reactions. Should have an S there, but whatever. Slower than benzene. Explain why the expected product is not observed, but only the actual products. Okay, this is a good one. So remember your actual mechanism. Is going to make a carbocation, right? Then you're going to get a rearrangement. And get this. This is what your reactive species is. Now, this problem is saying you would expect the benzene ring to react with it, right, and make this product. But instead what happens is you have chloride come back and react with it and make that. And the question is why? And so the answer is actually quite simple, and it's kind of given to you in the problem. But remember, it's observed that it reacts with electrophilic aromatic substitution slower, right? It's reacting slower. So the reason why is, I'll just call this molecule A, this molecule B. A reacts with slower than chloride does. So 2-chloropropane. Oh, I named that B, so I didn't have to write that out. Oh well. This is B. Is the product instead of the expected product. Basically, this electron withdrawing group makes the benzene ring react slowly enough, takes enough electron density out of the benzene ring. It's not nucleophilic enough to attack a carbocation. And so we didn't really cover this in lecture, but I thought that you knew enough to be able to figure this out. So that's the goal here. You can understand, hey, if chloride's coming back and attacking it, that means you're basically reforming this, meaning this thing ran around solution as a carbocation and then didn't react with the benzene ring, and then chloride eventually found it again and remade the product. Draw the energy diagram for all of these. So I always like to do this where you're going to have one intermediate and then a final product. And this will be A. Yeah, I'll do there. Okay. Let's see. B should react faster, right? Because the methyl's an electron donating group. C should react slower. So I'll do D. It should react even faster. Is it really going to be that low? Probably not. Actually, another one that has a red that works. And then C is going to react slower. Right? So that's the way those energy diagrams are go. Make sure you can draw your energy diagrams. All right, consider the following Diels-Alder. Which product is more stable? That's going to be the exo. Which product is formed faster? That's the endo. Which product is major? That's also going to be endo. Just some basic Diels-Alder stuff you should know how to do. React the best diene and the best dienophile. Okay, the best diene is going to be one that's locked in the S-cis and also has electron donating groups. So this is the best diene. The best dienophile is going to be the electron poor one. Should be this one. Right? So if I react the two, I'm going to get, let me just do the reaction over here instead of just draw the product. Don't worry about stereochemistry. Dr. Davis is not worrying about it. I asked him and he said, yeah, we're not worrying about that. I will show this wedge though, just to show it. So that should be your product. So if I draw this here, there's that. All right, that's the last problem on this practice exam. Good luck studying for your exam on Tuesday.